Okay. All right. So good afternoon. We are back to online lectures. We've come back a full circle, unfortunately. All right. So in the last lecture, we discussed the Ford-Fulkerson algorithm. And one of the questions that we ended at is how do we know or how do we find an X incrementing ST path? Right? So basically the way the algorithm works is it keeps finding X incrementing ST paths and keeps improving the flow until there is no X incrementing ST path, at which point you have a maximum flow by the theorem that we proved last time. Right? So the question is, how would we find such a path? And in this example, I think one of you pointed out that there is perhaps no X incrementing ST path. Okay, so turns out that in order to find an X incrementing ST path, we can construct a different digraph. And if that digraph has an ST die path, then that would correspond to an X incrementing ST path in the original graph, and vice versa. Okay, so does anybody have any thoughts on how we would construct such a digraph? So we are going to take the same set of vertices. Remember, an X incrementing ST path basically looks like this. Whenever you see a forward arc, the X value should be less than the capacity of that value of that arc. And whenever you see a reverse arc, the X value should be greater than 0. Okay. So we want to find such paths, but we want them to look like simple, just ST die paths. So directed paths from S to T in our auxiliary digraph. So this is going to be called the auxiliary digraph, and we will construct it using X and the capacity is C. Okay, so I'll use this notation for the auxiliary digraph. So does anybody have any thoughts on how we would construct the auxiliary digraph? Let me ask you a question. Should there be an arc between these two vertices? And if there should be, what direction should it be? Or should there be arcs in both directions?
So it should be from V1 to S.
From V1 to S. Right, that's true.
So we can undo that flow.
Exactly. So we will put an arc from V1 to S in this particular case. So let's just try to do this in this manner and then we will formalize things. So we'll put an arc from V1 to S because we can't send any more flow on this arc, but we can push it back. That is the intuition. Okay. What about S and V2? And I also want to label these as E1, E2, E3, E4. Okay. What about S and V2? Should there be any arcs or no arcs? Both arcs? One of them? Varun?
So it should be like,
yeah.
Yes, sir. So it should be like 3 back from V2 to S and 1 from S to V2.
Right. So we are not going to put any numbers. We are just going to construct a directed graph. So
Okay,
we
so
suggest
we'll have to.
both of them, right? We are going to put
labeling on both graph is different.
Labeling is different.
Vertex,
Thank you.
vertex.
Thank you. Thank you. Yes, that is right. So let me fix the labeling. The top two vertices are V1 and V2, and the bottom two vertices are V3 and V4. Yeah, so this should be, yeah. So this is V2 and this is V3. Thanks. And yeah, so what we are going to do in this case, between S and V2, V3, we are going to put both the arcs because the current value is 3 and the capacity is 4. So either we can push one more or we can pull back 3. Okay. So we're going to put both of these arcs here. Okay. Good. So hopefully the construction is now clear, right? So let's go one by one. V1, V2. We have the flow at 0 and the capacity is 1. So we can only push more flow on that arc. So this one will go in this direction. Okay. And that is corresponding to E1. Corresponding to E2, it's already at full capacity. So the only thing we can do is we can push it back. So that will also be directed in this way. So it's a directed graph with multiple edges. Okay. All right, let's look at V3, V4. We already have it at full capacity. So the only thing we can do is push it back. So this is corresponding to E3. And E4 is at 0 flow. So we can't, so we will keep it in the same direction only. Okay. And let's look at V3 to V2. It's at 2, which is less than 3. So we will put arcs in both directions. And the same thing happens with V1 to V4. And V2 to T, it's only going to be the reverse direction because it's already at full capacity. And V4 to T is going to be both ways. Okay. And this is what we are going to call the auxiliary digraph. And I will denote it as Hx, C because using X and C, we can construct it. Are there any questions or concerns regarding the definition? So observe that any X incrementing ST path will become an ST die path in the auxiliary digraph. Hopefully the construction makes that evident. Think of an X incrementing ST path and observe what happens in the direct auxiliary digraph. It will become an ST die path. And now do the reverse. For any ST die path, it will become an X incrementing ST path. It will correspond to an X incrementing ST path in the original max flow instance with the given flow X. Okay. And now we want to find out that whether there is an ST die path in this digraph or not. So that we can just do using breadth first search, right? Let's just do it for this example. So let's start at S. And what are the places we can go to? We can go to V3. So we will go to V3. From V3, we can only go out to V2. And observe that from V2, at V2 we have only incoming arcs except for the one which is going back to V3, which we have already visited. So using breadth first search, these are the only two vertices we can visit from S apart from S itself using ST die paths. Okay, so these are all the SV3 V2 is the set of reachable vertices from S using die paths. And let us see what this corresponds to in our original instance. So let us look at the cut corresponding to SV3 V2. Let's see. What does partial plus of u, where u is equal to S V3 and V2, look like? Okay, let's go here and let's look at all the arcs that are in this cut. So we want to go from S, V3 and V2 into the outside of this set, into the complement. So one of the arcs that we will pick is SV1. From V2 we can go to V1 and to T. And from V3 we can only go to V4 using E3. That is your cut. Does everybody agree? We have 4 arcs in the cut. And the capacity of these 4 arcs is 1 plus 1 plus 1 plus 1 is equal to 4, which is exactly the value of our flow right now, 1 plus 3. Okay. Are there any questions or concerns regarding the cut? So what are the, so I'll just write down what the final thing is. So observe that the capacity of the arcs going out of U into U bar is exactly equal to 4, which is exactly equal to the value of our current flow as expected. Right? And because there is no X incrementing ST path. So the observation, without proving it rigorously, hopefully you can all prove it yourself. Each X incrementing ST path in the given max flow instance with respect to flow X corresponds to an ST die path, in the auxiliary digraph Hx, C and vice versa. Okay, and the proof is do it yourself in case it's not already clear. All right, so now we can revisit the Ford-Fulkerson algorithm. Right, so we are given HSTC. So we will start with any flow. Start with any flow X. Possibly you could just take the zero flow. Right. And then you keep constructing. So now we have the following loop. Construct auxiliary digraph Hx, C. If Hx, C has an X incrementing, ST die path. Yeah. Has an ST die path. Let Q denote the corresponding X incrementing ST path in the given instance. Okay, And in this case, we will simply increment obtain x prime from x as per the proposition we discussed last time. Okay. And if there is no such path, then let U be the set of all vertices reachable from S in the auxiliary digraph using dipaths. Okay, and at this point we simply return the, okay, and I should set x back to x prime, and we return x and the set U. All right. Any questions or concerns? All right, and as we noted last time, the total number of loop iterations is upper bounded by the, assuming that you have integral capacities, the total number of loop iterations will be upper bounded by the flow value for a maximum flow, right? So if capital F is the maximum flow value, then number of incrementations is at most these many, because every time you will increase the flow by at least one, you will always be making integral changes. So you will take at most that many steps to get to the maximum flow, right? We have one more thing now. We are constructing the auxiliary digraph. Well, constructing the auxiliary digraph is not too difficult. You just have to look at every arc. So the time it takes is simply order of number of edges or number of arcs. Okay, so this step is simply that much time, and so the total time complexity is the order of the number of edges, the number of arcs, sorry, times the value of the maximum flow. Okay, and that is, are there any questions or concerns regarding any of this stuff? Yeah, so this is basically theorem 3.9. Okay, so observe that the time complexity of the Ford-Fulkerson algorithm depends on the value of the maximum flow, right? So can we get rid of this dependency? The time complexity sorry. I did not mean to put the absolute value, just too used to it, sorry, because this is simply the value of the maximum flow, which we know is going to be non-negative because all the capacities. So this is assuming integral capacities. In fact, this is also true for rational capacities. by a trick that we did earlier. So in fact, I'll just put assuming rational capacities. This is still true. You just have to multiply by a big enough number, right? So it will still depend on the flow value. All right. So the question is, can we get rid of this dependency where F is the value of maximum flow? In other words, can we get an algorithm that depends simply on the number of vertices and the number of arcs? So the answer is yes, but I'm not going to cover this. I'm just going to tell you how you do it, but I'm not going to cover it because I would rather cover other things in this course in the remaining time that we have. So it's a famous algorithm called the Edmonds-Karp algorithm. The algorithm is very simple once you know the Ford-Fulkerson algorithm. It simply says, rather than choosing any ST-die path in your auxiliary digraph, you choose a shortest ST-die path. Okay? So that will correspond to a shortest X incrementing ST path in the original instance. And if you always choose shortest paths, then you need some analysis. The analysis is the difficult part. The algorithm is very easy, but there is an analysis that shows that now the time complexity will not depend on capital F anymore. It will depend simply on the number of edges and the number of vertices. And that is called the Edmonds-Karp algorithm. Okay. So I'm not going to prove this because I want to focus on other things. So the answer is yes. And that brings us to Edmonds-Karp. This is from 1972. However, also it's popularly known as Edmonds-Karp. However, it was already known to Dinitz in 1970. Okay. It's the same as Ford-Fulkerson. Except that you choose a shortest ST-die path at each step in the auxiliary digraph. Right? And that will correspond to a shortest X incrementing ST path in your original graph. Okay. So the algorithm is very simple. And I'll just state the time complexity, which requires a proof, and I'm going to skip that. So it's, yeah. It's order number of vertices times number of edges, number of arcs squared. Okay. So the one occurrence of the number of arcs is coming from constructing the auxiliary digraph. But the main point is that the total number of incrementations will simply be the number of vertices multiplied by the number of arcs instead of the capital F, which was the maximum value of a max flow. Okay. So this requires careful analysis and proof. It's non-trivial. I remember covering it in advanced graph algorithms. So if you are interested, you can take a look at my advanced graph algorithms course and find it in lecture 22 or 23. I don't remember exactly. So it's covered in multiple other courses, which is why I don't want to spend time on going into the analysis and proof of Edmonds-Karp algorithm. Okay. Are there any questions or concerns at this point? Has anyone seen the Edmonds-Karp algorithm in another course? Maybe Neha?
Yes, sir, in ADSA it was taught.
ADSA also you have seen it? Okay.
Yes, sir.
Yeah.
Even in BTech we were taught this in design analysis.
Great. Great. Okay. All right. Anyone else?
Advanced graph algorithms.
Right. Which you are taking currently, right?
Yes.
Yeah, exactly. Yeah, so that's another reason I don't want to cover it, because some of you have either seen it or you are seeing it or you will see it soon. Okay, so it's covered in multiple courses, and let's not spend time on that in this course. Okay. Something's wrong with my OneNote. Okay. Okay. All right, so that's all about Edmonds-Karp and Ford Fulkerson. I want to complete a statement that I forgot to complete last time. So I was going through the notes and I realized that I had forgotten to complete a theorem statement. And I also made one mistake towards the end, so I would like to correct that. Give me 1 second. Yeah. So last time we discussed, we proved theorem 3.6. And I left the statement incomplete. So I'm just going to write it down again. So we are in the standard setting. We have a max flow instance. And we have NST flow. And what we proved is that if there is no X incrementing ST path, then blah, blah, blah. And this is the part that I did not fill up later. The conclusion was that X is a maximum ST flow. And the way we proved it is basically what I want to write down here. What we did is we proved that the following set is the desired cut. It is an ST cut whose capacity is exactly equal to the value of the flow we are looking at. And how did we define it? We looked at, so U was defined as the set of all vertices reachable from S using X incrementing paths. Right? By assumption, T will not be in this set, and we showed that this is the desired ST cut. So this is an ST cut whose capacity such that its capacity is exactly equal to the value of our flow. And that in particular proves that the given flow is a maximum ST flow. Okay. In fact, I should say it is an ST die cut to be very clear. Okay. So I forgot to write this part. In fact, we also, this theorem directly proves the max flow min cut theorem. I think I mentioned that the algorithm that we discussed implies the max flow min cut theorem, but the algorithm only terminates for rational capacities, at least the Ford-Fulkerson algorithm, right? So a better way to prove the max flow min cut theorem is by directly using this theorem. So theorem 3.5 is the max flow min cut theorem. All right, so I wrote the statement last time. I'll just write down the proof. Let's say X is a maximum ST flow. Right? Now that means that there can't be an X incrementing ST path, because if there is an X incrementing ST path, then we know that we can improve the flow by choosing a value beta and then adding and subtracting as we did, right? So automatically this means that there does not exist an X incrementing ST path, right? But then the theorem statement is telling us how to get the cut whose capacity will be exactly equal to the flow value, right? And now by theorem 3.6, partial plus u as defined there is has capacity exactly equal to the flow value, right? And therefore it has to be a capacity cut of minimum capacity, because if there was a cut of lower capacity, then that would contradict the flow value being whatever it is, right? So this proves the max flow min cut theorem without any assumptions of integrality or rationality or anything. All right. Okay, so that is the thing I wanted to correct. Are there any questions or concerns? All right, if not, see. All right, so for the rest of today and tomorrow, Wednesday, I want to show you a proof of the max flow min cut theorem using LP duality, right? Because we mentioned that this is basically applications of duality. So we have seen a combinatorial proof, and I would like to show you a proof using LP duality that you are unlikely to see in other courses. All right. So let's start a new page. And all right, so max flow min cut theorem via LP duality. Okay, and we will also have to use integrality and everything. So a lot of things will come together, and we will prove the max flow min cut theorem using all of these things, not just duality but also integrality. So totally unimodular matrices. And this is similar to one of your assignment 5 problems, where you will be proving the Koenig-Egervary theorem using LP duality and integrality concepts. All right. Are there any questions or concerns before we start on this journey? All right, so let's say we are given a max flow min cut instance, HSTC. All right, so I want to start by making an assumption which we discussed earlier, but until now we did not use that assumption. Today we will use that. So we are trying to send flow from S to T. So it is kind of natural to assume that S only has outgoing arcs and T only has incoming arcs. So that is the assumption we are going to make, and I'm going to explain to you why that is a safe assumption. So this is the safe assumption. Let's see why. Supposing you have a situation where S has both outgoing arcs and incoming arcs. Okay, let's say the capacity is 3, 2, 1, and 6. I claim that I can create another instance by adding an extra vertex, so that the S vertex in that one, I will call it S prime, it will only have outgoing arcs. Okay, and the trick is as follows. I will create an extra vertex S prime, and S will remain as it is. And between S prime and S, I will just put one arc like this. Observe that the maximum flow value in this case will be at most 3 plus 2, 5. So I will put a capacity of 5 over here. In some books, they put a capacity of infinity, but I never considered infinity capacity because I wanted to not deal with them. So I'm just going to choose 3 plus 2 equal to 5 in order to make this work. And I claim that whatever the maximum flow value is on this instance will be the same as this one, and the same thing for minimum cut. If there is a min cut in the first instance of a certain value, you will be able to find a min cut in the second instance of the same capacity. Okay, I won't prove this, but you can do this. This transformation preserves the max flow value and min cut capacity. Okay, and I can do the same thing for the sink vertex T. Okay, so therefore I can make this safe assumption. This will just simplify life a bit. We won't have to deal with too many complications if we make this assumption. Are there any questions or concerns? All right, so with that one assumption, let us try to prove this using LP duality, and we won't finish it today. Let us write down the primal LP and the dual LP and see how far we can get today. All right. All right, so we have written the primal LP before. It is the following. Let me actually leave some space so that we have more space to write. Yeah, let's start here. So you may recall that we wrote down the primal LP as follows. Let me just remind you what things are. So for every arc, you need to figure out what is the X value. So we have an X variable for each arc in the digraph, right? And the matrix A was the vertex arc incidence matrix. And we deleted two rows, one for the vertex S and one for the vertex T. And this Ax equal to 0 represents the conservation constraints. And the second part, 0 less than equal to x less than equal to c, it represents the non-negativity and capacity constraints. Or you can think of it as simply the capacity constraints together. Okay, and the vector d is basically calculating. So this quantity is basically this quantity, right? So for all the arcs that are going out of S, we are going to add up the flows. So that is how we get the vector D. For each arc which is incident at S, these are only outgoing arcs by our assumption. We will put a +1 over there, and the rest will be zeros. Okay. Are there any questions or concerns regarding the LP? We wrote this earlier, right? And we observed that this LP, its feasible region is going to be integral. In particular, there will be an optimal solution which will be integral. So that will be your integral maximum flow. Okay. We noted that feasible region is integral, which implies there exists an optimal solution that is integral. All right. I want to write the dual of this, but notice that this is not in the format that we are used to. So let us put it in the format that we are used to. Okay. So maximize D transpose X, and let me write it like this. Ax equals 0 and X is at most C and X is greater than equal to 0. And I would like to combine these two into a single matrix vector constraint. Okay, how do we do that? That's not too difficult. Maximize D transpose X, subject to, we'll put the A matrix followed by the identity matrix multiplied by the vector X, and the constraints corresponding to A will be equality, and the constraints corresponding to the identity will be less than equal to. On the right hand side, we have 0 vector followed by C. Any questions or concerns? Is everybody able to visualize what we just did? Okay. So now this is in a format that we are used to. We have a maximization, we have non-negativity constraints, and we have a single matrix vector capturing all the other constraints. Okay. So now it's easy to write down the dual. Okay. So let's do that. So maybe I will just write it here, because I will write the dual multiple times in order to understand what it's trying to say. So we're going to have a minimization problem. Okay, before we write down, observe that for each constraint or for each equality constraint, we will have dual variables. Let's call them the y variables. And for each less than equal to constraint coming from the identity matrix, we will have z variables. Okay. Let us try to figure out how many y variables we have and how many z variables we have. Can anybody tell me how many y variables do we have? How many rows are there in the matrix A? Remember, the matrix A is the vertex arc incidence matrix, and we remove 2 rows. So how many variables do we have? Y variables?
Number of vertices minus 2.
Yes, exactly. So we have a Y variable for each vertex except for S and T. And we have a Z variable for each arc, right? Because the number of rows in the identity matrix will be exactly equal to the number of columns, which will be exactly equal to the number of arcs in our graph. And a Z variable for each arc of the graph. Maybe I should say each V in this and each E in this. All right. So, and now let's look at the dual. So we will have minimize 0 transpose Y, which will be 0, plus C transpose Z. So we will just have C transpose Z over here, subject to, let us transpose this matrix. So we have A transpose I transpose. And then we have Y and Z. And on the right side, we have the vector D. You should check on your own later, maybe, that all the dimensions match up. It's simple recipe to write down the dual that we are following. Okay. And what about these constraints? What do these constraints look like? What should I put over here? But we are going to look at these variables. They are non-negative, so that's natural. And for a minimization problem, the natural will be greater than equal to. Okay. And the Y variables are going to be free. And the Z variables, they come from the less than equal to constraints, which are natural for the primal, for the maximization problem. And so the Z variables will be non-negative. Okay, let us write it down once again in a different way. So this is minimize C transpose Z subject to A transpose Y plus Z greater than equal to D. If you think about how the matrix multiplication works, you will get exactly this. Okay, and Z's are non-negative. Okay. So this is one way to write the dual. So we have written it in 2 different ways. The second way is particularly interesting because in a previous lecture we discussed that any LP that looks like this, where the A matrix is totally unimodular, it will be, the feasible region will be integral. So I'm using over here a certain theorem that we discussed by theorem 5.10, statement number 3. This is from GKT. This we discussed, I think, in lecture 45 or 46. The feasible region of the dual LP is also integral. In particular, there exists an optimal solution that is integral. All the hypotheses you can check of the theorem statement number 3 are satisfied. So we can make this conclusion. So at this point, we know that the primal LP also has an optimal solution that is integral. The dual LP also has an integral optimal solution that is integral. Okay. The primal one we know is a max flow. So the optimal solutions that are integral basically correspond to integral max flows. Right. The dual LP, we don't know how to interpret it yet. is it really capturing the min cut problem? It's not immediately clear. So what I would like you all to think about is I want you all to think about the dual LP and see if you can yourself figure out that this captures the min cut problem. It's not easy. I'm going to give it as a try it yourself, and we will do it next time. So examine the dual and see if you can figure out that it captures the min ST die cut problem. Okay, it's non-trivial. You need to really examine it closely and figure out what's going on with respect to each vertex. I will give you a hint. Break the set of arcs into 4 types of arcs. One is the regular arcs which are not incident at S or T. The other is the edges coming out of S. Then there are the edges going into T. And finally, there could be an edge going from S into T. So this is like this kind of arc. It may or may not exist in your graph. These are the edges going out of the arcs going out of S. These are the arcs coming into T. And these are all other arcs. So if you examine all of these kinds of arcs separately, you might be able to make some progress on this problem. Okay, so try it out and we will complete it next time and complete the proof of the max flow min cut theorem using LP duality and integrality. All right, are there any questions or concerns? Okay, if not, feel free to leave the meeting. So I'm going to stop recording now.